Okay, get this. What if everything we thought we knew about computer science was wrong? Because in 2025, that's kind of what happened. We're talking 3 breakthroughs that were considered literally impossible. We've got an undergrad who proved a genius wrong, a huge leap in the quantum race. You're going to want to see this. Let's dive in.
So let's just start there. Think about it. What actually happens when the so-called unbreakable laws of computing just, well, break? And I'm not talking hypothetically here. This is exactly what we're about to get into.
Yeah, because that is exactly what happened. In just this past year, we saw 3 discoveries that totally rewrote the rulebook on, well, everything. How we store data, how quantum computers can actually be built, even the absolute basic limits of computation. It's wild.
All right, first up, let's talk about something that's literally everywhere: data storage. We're going to look at a total revolution in something called a hash table.
So, to get your head around hash tables, you kind of have to stop thinking like a person. You know how we like things neat and organized, a library, right? Well, for a computer, the most efficient way to store and find stuff is to basically just throw it all on the floor. I know, it sounds completely chaotic, but trust me, this random mess is the secret sauce behind so much of modern software.
And for decades, this whole system had one massive trade-off. It was a constant battle between time and space. See, the fuller you made the table, to save space, the slower it got. It had to look for an empty spot. And if you had a table with, say, 1 million items, finding a spot for that last item could mean checking 1 million different locations. It was a huge bottleneck.
And listen, this wasn't just like a best practice. It was basically gospel. The original method from the 50s just used randomness to find the first open slot. Simple enough. But then in 1985, Andrew Yao, we're talking a Turing Award winner, a legend in the field, mathematically proved that this was the best way, the absolute optimal solution. And for 40 years, that was it. The case was closed.
And then along comes Andrew Kerpiven, an undergrad, a student at Rutgers. He's just tinkering away on some research for a professor, and he stumbles onto something that, well, it just shouldn't exist. A hash table that completely breaks Yao's 40-year-old unbreakable proof. I mean, you can't make this up. It is the definition of a David and Goliath story for computer science.
So you're probably asking, how on earth did he do it? It's actually so clever and simple. Instead of his algorithm just blindly grabbing the first empty spot it sees, it looks ahead a little bit. It finds a spot that's more strategically valuable and claims that one instead. And the result? It's insane. The searches become super fast. We're talking a query time that basically stays the same, even if the table is crammed 100% full. Which leads to this stunning conclusion. That whole fundamental battle between time and space? Yeah, it was never real. It was a myth.
All right, from one revolution to the next. For our second breakthrough, we're leaving the world of data storage and diving headfirst into the seriously mind-bending universe of quantum computing. And specifically, we're talking about a problem so big, they call it the quantum chasm, the problem of noise.
Yeah, this quote really nails it. See, quantum bits, or qubits, are unbelievably powerful, but they are also ridiculously fragile. A normal computer bit is simple, right? It's either a 0 or a 1, on or off. But a qubit, it can be a 0, a 1, or kind of both at the same time. It exists on this whole spectrum. And that means it's not just right or wrong. There's a whole spectrum of ways it can be a little bit off. A single tiny error, a little nudge, can completely derail a calculation that's trillions of steps long.
So, for a long time, the best idea on how to fix this was a technique called the surface code. The basic concept is pretty cool. You take a whole bunch of those fragile physical qubits and make them work together as a team. By sharing information and checking each other's work, they combine to form one super stable, high-quality logical qubit. Think of it like a bunch of shaky singers who, together, create one perfect, unwavering note.
But, and this is a big but, here was the massive roadblock. For years, every time scientists tried to do this, every time they added more physical qubits to make the team bigger, the errors actually got worse. It was like adding more singers, just made the choir sound more out of tune. The noise from all the new parts just overwhelmed the whole system. It was so frustrating. It felt like taking 1 step forward and 2 steps back, over and over again.
Until now. This year, everything changed. Google's quantum AI team fired up their new 72-qubit processor, which they call Willow. And what they saw was historic. For the first time ever, adding more qubits made things better, exponentially better. As they made the code bigger, the error rate was cut in half.
Then they made it bigger again, and the error rate was cut in half again. This was it. They had finally, actually crossed that quantum chasm.
And this wasn't some tiny improvement they had to dig for in the data. It was immediate. It was obvious. On the very first run, they saw a 40 to 50% improvement in error suppression. Can you just imagine being in that lab, after years and years of failure, watching those numbers come in, knowing you're witnessing history?
So what does this all mean? It means that, for the first time, we have real, physical proof that we can beat the noise, that quantum error correction actually works in the real world. This isn't just a small step, it's a giant leap. It gives us a clear roadmap, showing that these massive, world-changing quantum computers, they're not just science fiction anymore. They are physically possible to build. Okay, for our final breakthrough, we're going even more fundamental. We're heading into the pretty abstract world of complexity theory. This gets to the very heart of what computing is. The two most basic resources you have: time and space, or, memory.
Now, for as long as anyone can remember, there's been this simple, intuitive rule. It basically says that the amount of time an algorithm takes to run is pretty much tied to the amount of memory it's going to need. If a calculation takes T amount of time, you'll probably need about T amount of space. Made sense, right? Everyone just sort of accepted it as a basic law.
And then, an MIT researcher named Ryan Williams came along and just blew it all up. He proved it was wrong. And the reaction from other computer scientists wasn't excitement at first, it was just pure shock. This quote here says it all. The idea was so out there, so revolutionary, that even the experts who understood the math, they just flat out didn't believe it could be true.
So get ready for the new rule. Williams proved that any computation that takes T amount of time can actually be done with only about the square root of T in space. Now let that sink in. That's not just shaving off a few percentage points. This is an exponential savings. It's a game-changing leap in what we thought was possible for efficient computing.
And the genius part is how he did it. He was looking at an existing algorithm for something called tree evaluation that had this clever trick for reusing its own memory over and over. And he had this aha moment where he realized this isn't just a one-off trick. This technique could be turned into a universal simulation, one that could work for basically any algorithm out there. And the result of that realization, well, our entire understanding of computational efficiency has been turned on its head, completely.
So let's just recap the new rules of the game for 2025. Rule 1. That old trade-off between time and space and hash tables? It's gone. It's not a thing. Rule 2. We finally have a practical, scalable way to build quantum computers that can actually fix their own errors. And Rule 3. Any computation you can think of needs exponentially less memory than we ever thought was possible.
Just think about that. 3 foundational beliefs, things that were considered law, all shattered in a single year. It just makes you wonder, right? What supposedly impossible rule is going to be the next to fall? We don't know the answer, but one thing is for sure.